Hi, my name is Adiabatic. I am a graduate student at Wayne State University. We are going to be doing an example from ME7290, Advanced Combustion and Emissions 1. The example we're going to be covering is adiabatic flame temperature. So there's two methods. Method one is constant pressure. Which is where our enthalpy of our reactants is equal to our enthalpy of the products. Method two focuses on constant volume. And that is where internal energy of the reactants is equal to internal energy of your products. So we're going to focus on the constant pressure. So for constant pressure, as we can recall, our H reactants as a function of temperature and pressure is equal to enthalpy of products as a function of temperature and pressure. And if we were to do this on a per mass basis, you would divide by mass. So H little h is equal to H over M. So this would give us HR is equal to HP. And that when we sum, because we're on a per mass basis, we have HR of the reactants times the number of moles is equal to the sum of HP times the number of moles. So another way to look at this is we have enthalpy. On the Y, we have temperature. On the X, we have our reactants, we have our products, and if we are to draw a line from our reactants to our products are going to start out with our T at a reference temperature, or T initial. And we're going to take it over to the products, which is our T adiabatic, which is what we'll be solving for. So one thing to note is your HR of reactants is equal to H of P, which is what we stated prior. So another way we can write HR is equal to HP. We can also write this as HR minus HP equal to 0. All right, so let's consider first the law of thermo. We have our heat transfer is equal to our internal energy plus the work of the system. So let's look at mechanical work first. That is equal to P dV. And if we consider our equation above, we can also write du as dH minus P dV. So if we were to sub in our du to the equation above, we would get our heat transfer is equal to dH minus P plus PdV from our mechanical work. These would cancel, and we are now left with heat transfer is equal to our enthalpy. So now that we have this background, let's get into the problem. So the problem we are going to be working on is adiabatic flame temperature. For complete combustion. So our example that we're going to look at is going to be methane as it reacts to air. So we're going to say CH, which is our methane, plus O2. And for every O2, we have 3.77 nitrogen. That is our reactant side. And then we have our carbon dioxide, our H2O, and our N2. So the first thing we're going to want to do is balance our equation using stoichiometry. So if we look at carbon first, on the reactant side, we have 1. And on the product side, we have 1. So we're going to put a 1 in front of CH4, a 1 in front of CO2. So next, we are going to balance our hydrogen. So on the reactant side, we have 4 hydrogens. And on our product side, we have 2. So in order to balance this, we would need to put a 2 in front to then get 4 hydrogens. And then next, we will balance our oxygen. So on the reactant side, we have 2 oxygens. And on our product side, we have 4. We have 2 oxygen coming from the carbon dioxide, and we have 2 oxygen coming from the hydrogen, or the water, the H2O. So in order to balance this, we're going to have to multiply on our reactant side by 2, because that's not equal, so we'll say 2 times 2 is equal to 4, so that checks out. All right, and then for our nitrogen, our final, we have 2 times 3.77 on the reactant side, and then we also have N2. But we're going to leave these the same because we also have N2 on the other side. So in order to balance this, 7.58. So now that we have this balance, we are going to recall our first law of thermo. We had heat transfer is equal to dH, our enthalpy. Now, assuming adiabatic, what does that mean? That means we have no heat transfer. So our equation is now dH is equal to 0. All right, so there's 2 methods for solving for the enthalpy. First method, we have our delta HI of T is equal to our heat of formation at our reference temp plus our delta HI of T. So this HI can also be written as HIT adiabatic minus HI at T reference. So if we were to plug this back in, our delta HI is equal to HIT adiabatic. Now this works great for simple cases and solving using a computer program. However, because we are solving this by hand, we are going to use the second method, which is delta HI of T is equal to the heat of formation at reference temperature, or TI, plus delta I. Now, instead of writing our delta HIT as we did prior, we are going to write this as a function of temperature. So we're going to look at CP is equal to DH over our temperature. And we can rewrite this as CP dt is equal to DH. So that will then create the equation HIT, delta is equal to your heat of formation plus CP delta T. And that delta T, again, is going to be your T adiabatic minus your T reference. So, if we recall the equation, the sum of Ni HR is equal to the sum of Ni, which is our moles, of HP. We are going to be at our T reference temperature of 298 Kelvin. So when we grab our CP values from the tables, we are going to be using 1,200 Kelvin. And why, you ask, we're grabbing this 1,200 Kelvin? This is a typical temperature that you would see for a combustion. And we are going to take that 1,200 Kelvin and take an average of it in comparison to our adiabatic temperature that we're trying to guess. So if you are to solve this out for T adiabatic, our first guess is 1,200 K times 2 minus 298 Kelvin, which is equal to 2,102 Kelvin. All right, so I'm going to write up the values for our species. I'm going to write our heat of formation, which will be in kilojoules per kilomole. And then we have our CP values at kilojoules per kilomole Kelvin. All right, so here are the values that come from the thermodynamics table. Our HF, which is our heat of formation, this comes from the top of the tables for methane, CO2, and H2O. And the reason N2 and O2 are 0 is because these are in their standard reference. and then this, 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 and then the same thing for the CP values. We're only going to see CP values for CO2, H2O, and N2. So we're going to start out with our reactant side. And if we remember, we let TI equal 298. So HR is equal to the number of moles of CH4. Heat of formation for CH4 plus the CP for CH4, TI minus 298. And then we're going to do the same thing for our O2 and our N2 on the reactant side. All right, so if we remember from the table, our heat of formation is 0. For O2 and N2, since our TI is 298, this is going to go to 0 as well. So then now on your reactant side, you are left with the number of moles for CH4 times the heat of formation of CH4. So if we are to pull, if we remember back to our stoichiometry, our number of CH4 is 1 kilomole. And our heat of formation that comes from the table that we previously had is negative 74,831. All right, and now we are going to look at our product side. So on our product side, we have CO2, H2O, and N2. All right, so if we take our number of moles of CO2, we're going to multiply it by our heat of formation of CO2, adding our CP values of CO2, and then within that, we're going to multiply it by T adiabatic minus 298, which is our reference temperature, and then you will repeat the same process, adding your H2O and your N2. All right, so now if we were to go back to our equation and plug in the values for our CO2, H2O, and N2 for the CP values, remembering how we balanced our equation, it's pretty much plug and chug from this point. So we're going to have for CO2, our CP value for CO2, and then we're going to look at it from T adiabatic minus 298. And then you'll do the same for your H2O and your N2 on your product side. Now, if we're to simplify this equation, we're going to get negative 877,236 plus 397, and we are going to multiply that by T adiabatic minus 298. And now we're going to set that equal to our reactant side. And by doing so, we're going to get negative 74,831 on our reactant side is equal to negative 877,236 plus 397 T adiabatic minus 298. And if we move everything to one side to get T adiabatic on its own, we're going to get negative 74,831 plus 877,236 all over 397, and then we're going to add our 298. And this is going to give us T adiabatic 2319 Kelvin. And that concludes our problem. Thanks for watching.